Hello everyone, I'm Richmond Roy Rodriguez, a recent graduate of Bachelor of Science, major in Electronics Engineering from Ateneo de Manila University of the country, Philippines. So today I will be presenting about the research that I did along with Ms. Ruby Jane Mapolon and Dr. Rosela Reyes entitled A Non-intrusive single-channel abdominal fetal electrocardiogram monitor using singular value decomposition. So to start, let us talk about maternal health. World Health Organization defines maternal health as the health of women during pregnancy, childbirth, and postnatal period. Each stage, according to them, should be a positive experience, ensuring women and their babies reach their full potential. Now, in our country, we have this law, Republic Act number 10354, also known as the RH Law, which is intended to guarantee universal access to contraception, fertility control, sexual education, and maternal care. Following this law, there are efforts in improving prenatal care, childbirth care, and maternal care services in health centers in our country. Now, in addition, there are devices such as fetal Dopplers that can be used at home to monitor the heart rate of the baby. So as you can see, there are existing systems and devices in our country that pregnant women can use for their maternal health. Now, what is the problem? According to the latest data from the UNIGME, the neonatal mortality rate in the Philippines is 13.3 per 1,000 live births in 2019. Although there is significant improvement through the years from the 25.7 in 1970. However, the current rate, 13.3, still falls short of the United Nations Sustainable Development Global Goal of 12 per 1,000 live births by 2030. Now, according to our research, one of the leading causes of infant death is congenital anomalies, whereas 30 to 50% are from congenital heart diseases. This was the main motivation of our study. Secondly, maternal and prenatal health care in our country is highly concentrated at the densely populated cities. This hinders women in the more marginalized settings such as rural areas from getting the proper care they need. So the main objective of our study was to develop a cost-effective prenatal monitoring system that can process the raw ECG data and display the resulting fetal ECG. Specifically, we have these three main points. First is to gather abdominal signals using the monitoring device. Second, to process the obtained signal and extract the fetal ECG. And third is to validate the obtained fetal ECG compared to global standards. Now, let us move on to the review of related literature. The first study is entitled Fetal ECG Extraction and Enhancement in Prenatal Monitoring, Review and Implementation Issues. Now, in this study, they checked and reviewed four categories of extraction algorithm, namely blind source separation, template subtraction, adaptive method, and hybrid. And according to their results, blind source separation is the most efficient with nearly 97.47% accuracy. Now, just some more points about blind source separation. So, the three most common methods under blind source separation are singular value decomposition, principal component analysis, and independent component analysis, with all the assumptions that signals are statistically independent from each other, and it requires large number of ECG leads to have adequate results. The second study, fetal ECG extraction from single-channel maternal ECG using singular value decomposition. So this outlined the use of singular value decomposition or SVD in the fetal ECG extraction. In essence, SVD is used to decompose information matrix into orthogonal component modes. In this algorithm, they also use singular value ratio spectrum to estimate the period of the most dominant periodic component. So in the general process, they use the obtained estimated period in order to arrange the data into matrix A, and then they perform SVD to get the most dominant periodic component, and they separated it. So that most dominant periodic component should be the maternal ECG. Now, they perform it once more in order to get the second most dominant periodic component, which should be the fetal ECG. So, according to their paper, they were successful in extracting this fetal ECG from the single-channel composite maternal ECG despite the low signal-to-noise ratio. The third study is entitled A Real-Time QRS Detection Algorithm, or more commonly known as the Pan-Tompkins algorithm, which is an algorithm to detect QRS complex from ECG through three parameters: slope, amplitude, and width. So, in this study, they also mentioned a method of detecting peaks through a series of filters, which will be which was an inspiration for our methodology later. Okay, so according to their study, they were able to get an accuracy of 99.3% in the QRS complexity detection. The last study is entitled an open source framework for stress testing non-invasive fetal ECG extraction algorithms. So in their methodology, they use a total of 145.8 hours of multi-channel data, and they tested the four methods mentioned earlier as well in the first literature. So they use a statistical parameter set by ANSI/AAMI/ISO to measure accuracy of the extraction algorithm. And these are the three parameters: sensitivity, positive predictive value, and the F1 accuracy measure, which is derived from both sensitivity and positive predictive value. Now, according to the result, blind source separation is still the most accurate with an accuracy of 99.9%. Now, let us move on to our actual methodology. This is the block diagram of our methodology. Essentially, we have three major points. So the first one is the monitoring device, which will be used to gather the signal. And then we have the signal processing, which was used to extract fetal ECG. And lastly, validation. Essentially, we validated both the output of the monitoring device and the signal processing algorithm. For our monitoring device, we use an existing device from Maxim Integrated, which is the Max ECG monitor. So this is a wearable device that can detect various parameters like movement, temperature, and in our case, ECG and heart rate. So actually, this device is more commonly used in physical training, fitness programs, applications. So we use this opportunity to also test this device in the medical application. This device is based on the MAX 3003, which is an ultra-low power single-channel multi-sensor device that can do real-time monitoring and can be connected to devices using Bluetooth. This also runs an open API, which means that further algorithm can be built upon this. So this is an overview of our data collection system. As mentioned, our main device would be the Max ECG monitor, and this would be connected to the abdomen of the pregnant women, and then we set by default the sampling rate at 125 megahertz, and the signal to noise ratio according to the device specifications is 80 dB. Okay. So after we connected this to the abdomen of the pregnant women, it will be connected to Bluetooth and will send the data to our Android application. Now let's talk about that Android application. So for the development, we use Android Studio and the language Java. And we intended this mobile application to perform three main functions. First, to interface with the max ECG monitoring device through Bluetooth. Second, to perform the signal processing to extract the fetal ECG. And third, to serve as a graphical interface between the user and the system. And in this right part, we can see the data flow diagram inside the application. So the raw ECG data will be obtained through Bluetooth, and the our application will perform the signal processing in order to extract the fetal ECG, and this fetal ECG can be both displayed with an image and can be exported through a CSV file for further research and for archiving. Now let us talk about our signal processing. So for this, the base method that we use is singular value decomposition. And here is the outline of the general procedure. So first, we apply three filters: derivative filter, square function, and moving window integration filter. And second, we use dynamic threshold to detect signal peaks. Third, we obtain the period length by getting the mode of all the differences between each peak. So as you can see, the first three steps is more on the obtaining the period length, which we change from the second study mentioned in the RRL. Instead of using the singular value ratio spectrum, we opted to adapt the peak detection part of the Pan-Tompkins algorithm in order to detect the peaks, and then we use mode in order to estimate the period of the most dominant periodic component. So after getting that, we interpolated or extrapolated segments of the original signal with lengths not equal to obtained period, and then the next parts would be the same with the second study from the RRL. So this is the general procedure for SVD algorithm. So we created an M by N matrix A, where N is the obtained period length. We performed SVD on that matrix to get the most dominant periodic component, which is the maternal ECG. And then we reverse the perform interpolation and extrapolation. And finally, we subtracted that maternal component from the original signal to get the first residual signal. So after that, we repeated steps 1 to 8 in order to extract the fetal component at step 6, and then the final residual signal at step 8, which should contain the noise and the interference. Finally, for our validation, so as mentioned, we validated both the device output and the signal processing. So for the device output, parameters were used to characterize the data gathered from the device, specifically the gestation period and the position of the device in the abdomen of the pregnant women. The output were compared to corresponding available ECG samples in the online database Visionet. Now, for our signal processing, we adapted the testing framework mentioned in the fourth study in the RRL. Specifically, we simulated signals from this tool, FECG Sim Toolbox, and we fed that signal to our signal processing algorithm and tested the results through these parameters mentioned as well: sensitivity, positive predictive value, and F1 accuracy. Now, for the specific data signals, we chose 5 simulated events. So baseline, no noise, no events. Case 0, no events but have noise. Case 1 with fetal movement. Case 2 with MHR, FHR acceleration, deceleration, and case 3 with uterine contraction. Okay, so we generated these 5 cases 3 times with random vector cardiogram in the toolbox, and then we also applied the noise level 3 times in order to generate a total of 45 different signals. Okay. Now, before moving to our results and discussion, I want to align first that the validation performed were not as intensive as planned because of the pandemic brought by the COVID-19 virus. Okay. So, specifically, the group was not able to test the device on actual pregnant women because all our scheduled meetings with them were canceled because of the pandemic. However, we still believe that the data present in this study and the validation performed at the end is still enough to give merit to this study. So first, let me show you the Android application we developed. So the first picture, you can see the homepage where the user can scan for the Max ECG monitor and connect with it through Bluetooth. So once connected, the user will get this second screen where the user can enable the ECG. So once enabled, the device will monitor or gather data in real time and show it here below. After the user disables it again, so that this filter button will be enabled and the user can click it to start the signal processing method and extract the fetal ECG as you can see in this third photo. Okay, so the image of the fetal ECG will be displayed and there will also be a send button in order to export the data through a CSV file. Okay, so this exported data will contain the raw ECG, the maternal ECG, and the fetal ECG. Okay. Now, just to note, this image is not representative of the output of the study because um, this is not obtained from a pregnant woman. So these are only to show the basic functions of the Android application. So now for the validation of our fetal ECG extraction algorithm, we have the summary of F1 scores. First, let us talk about baseline and case 0. So as you can see here, we obtained an accuracy of more than 92% for both case 0 and baseline. And this shows that the proponents were successful in implementing the fetal ECG extraction algorithm and that the application and the signal processing works as the group expected. Right? However, just some notes here. You can see the fetal ECG detection rate is a bit lower than the MECG detection. And the group found two reasons for this. The first is the problem with the algorithm. So actually, the algorithm clips extra signal at the end, extra data that does not contain any MECG peak. Okay, so even if this clip data does not contain MECG peak, it might contain some fetal ECG peak. That's why some of the peaks cannot be detected by the algorithm. The second reason is that the ratio between the MECG and the FECG are so great such that little fluctuations in the amplitude of the MECG peak will create or will leave a significant effect in the residual signal, and these residual peaks can be falsely detected as an fetal ECG peak. So those are the two reasons for this lower FECG detection rate. Now for the remaining three cases, the group expected that this will be lower than the first two because we limited the study to a study of pregnant women with normal ECG. However, we did not expect that case 1, meaning the case with fetal movement, will have also a high accuracy. So from this, the proponents further hypothesized that given that the monitoring device is connected to a specific part in the abdomen of the pregnant women, the fetal movement will not create an impact in the fetal ECG detection or extraction. Finally, for the conclusion, a fetal electrocardiogram monitoring system was successfully developed. The fetal electrocardiogram monitor is capable of collecting signals, performing signal processing, and displaying the extracted fetal ECG. The program was validated through a testing framework for extracted fetal ECG algorithms and showed accuracies greater than 90% for baseline, case 0, and case 1. The overall accuracy for all the 5 cases is 81.31%. However, due to some uncontrollable factors, specifically the pandemic, the proponents were not able to test the monitoring system on pregnant women. So for our recommendation, it may be best to include testing on pregnant women. It is also highly suggested to look for partnership with hospitals for more efficient data gathering and validation. Second, to further improve the accuracy of the monitoring system, more robust algorithms may be looked into to cater to other cases such as the case 2 and the case 3. And they may also look to solving the issues I mentioned about the algorithm that cause the lower FECG detection rate. Lastly, future research may also look towards possible implementation of real-time FECG extraction. So that is all for my presentation today. Thank you everyone for listening and have a nice day.